Hello and welcome to today's lesson on velocity time graphs. Our learning objectives are to interpret velocity time graphs, use velocity time graphs to calculate the acceleration, and use velocity time graphs to calculate displacement. Just as a quick recap, what is the equation for speed? Pause the video if you need to. Speed is distance divided by time. If we need to rearrange that equation to find out what distance is, what would the equation for distance be? Again, pause the video while you work it out if you need to. Distance is equal to speed times time. Finally, what is the equation for acceleration? And again, pause the video if you need to. Acceleration is equal to the change in velocity divided by the time. I'm now going to ask you to sketch the following graphs in the back of your book. It's important to note this is a velocity time graph, not a distance time graph. What do you think a velocity time graph would look like if the object was not moving? Pause the video while you try and sketch your graph, and don't be afraid to get it wrong. And here you can see the answer. The line will always be at the bottom this time for a velocity time graph if there's no movement, because velocity is 0 and it's going to stay at 0. Okay, what would constant velocity look like for a velocity time graph? Again, you can pause the video while you do a quick sketch in the back of your book. For a constant velocity, the line will be horizontal with a fixed value for velocity. The faster the velocity, the higher the line, the slower the velocity, the lower the line. What would the graph look like if the object was accelerating or getting faster? Here you can see the object with a constant acceleration. The speed is consistently increasing. If you remember before, we talked about how the equation for distance travelled is speed times time. So if the speed is constant, then working out the distance is pretty easy. Here you can see speed times time is just the area under the graph. If the object is speeding up or accelerating, then the area under the graph will, instead of being a regular rectangle, be a triangle. Hopefully you remember from maths that the area of a triangle is just half base times height, in this case half speed times time. This picture shows the velocity time graph for a lift inside a building. The sections of the journey are labelled with letters A to E. In this graph, upwards velocities are shown as positive and downwards is negative. Use the graph to answer the following questions. Which section is the object not moving? Which is it moving up? And in which is it moving down? Pause the video while you write down your answer. And here you can see the answers. At A, C and E the object is not moving, B it's moving upwards, and D it's moving downwards. Now describe fully the velocity of the lift during B. If you just wrote 2 meters per second as your answer, remember that velocities always need a direction as well. In this case it would be upwards. Did the lift have the same speed when it was moving up and when it was moving down? Make sure you explain your answer. The answer is yes, both B and D have the same speed, but they are moving in the opposite direction. Now you need to find the displacement of the lift during section B. Make sure you show you're working out and don't forget to pause the video. Displacement is the area under the graph, so in this case it's velocity, 2 meters per second, times 4 seconds, 8 meters in total. The lift starts on the second floor at time 0, and each floor of the building is 2 meters high. Write a description for the lift's journey, including which floor it's at and at what time. Pause the video while you write out your description. Your answer should look something like this. The lift is stationary for the first 2 seconds, then travels upwards, remember direction is important, for 4 seconds and reaches the 6th floor. And then it stays there for 4 seconds, then travels downwards for 2 seconds, reaching the 4th floor, and then stays there for 2 seconds. What do you think is unrealistic about the graph shown here? In this example, the lift changes its speed instantaneously. The acceleration and deceleration are infinite and would create incredible forces on the person in the lift. For safety's sake, the speed would have to change at a much more gradual rate in order to avoid injuring anyone on the lift. The gradient of a graph with time on the x-axis tells you about the rate of change with time. The rate of change of speed or velocity with time tells you about acceleration. Acceleration is change in velocity over time. In this example, you can see that the velocity has increased from 0 to 40 meters per second, and it's increased by 40 meters per second in 4 seconds. So the change in velocity is 40, the time change is 4 seconds, therefore 40 over 4 gives us an acceleration of 10 meters per second squared. Now I'd like you to plot a velocity time graph for a remote control car using the information provided here. Use graph paper if you have it available, and don't forget to pause the video while you work through this. The graph should look like this, with velocity in meters per second on the y-axis and time in seconds on the x-axis. Make sure your graph fills more than half the page. See if you can find the deceleration of the car for the last 4 seconds of its journey. Its velocity decreases from 3 meters per second to 0, and therefore the change in velocity is minus 3 meters per second. Don't forget to pause the video while you work it out. With our change in velocity of minus 3 meters per second and our time period of 4 seconds, we've got minus 3 divided by 4, giving us an overall deceleration of minus 0.75 meters per second squared. Use your graph now to try and find the distance travelled in the first 4 seconds of the journey. Remember that you're going to have to break down the area under the graph into triangles and rectangles. So the car will travel 1 metre in the first 2 seconds and then another 2 metres in the second 2 seconds, for a total of 3 metres. That brings us to the end of today's video. I hope you found this useful, and thank you very much.